Hi, kids. This video is going to be a quick review of electromagnetism. This is a very important music because it talks about how electricity and magnets are related, hence electromagnetism. So let's go over some of the basics first. First thing you should understand that with with magnets you have a north-seeking pole and a south-seeking pole. So let's say I have a magnet like this, North Pole, South Pole. Remember, there's a magnetic field around it. The magnetic field points in the direction that a north pole would move. So it's going to point away from the north, like this. It would point towards the south, like this. And then there would also be field lines that kind of loop around like this. Okay. Remember, what is it about the bar magnet that gives it a magnetic field? It is these magnetic domains. So iron have these domains, which means the domains in a bar magnet are going to be lined up to complete this loop. So they're actually going to be pointing this way like this. And if all of the domains are lined up really, really well, then you have a super duper strong magnet. If some of the domains are out of alignment a little bit, then you have a little bit weaker magnet, which is why you don't want to heat a magnet, which is also why if you break a magnet in half, you still, if I was to break this magnet in half, I would still end up with north-south, north-south, because the domains here would still be lined up, and then here would still be lined up. If you have something that can be magnetized, but it's not magnetized, that just means the domains in it are all kind of random. Okay, but if you were to attach this to this, these domains would line up pointing this way, so that now this thing would become magnetized. If you left it attached to here long enough, it would probably become a little bit like a magnet. But if you took it off, the domains are going to get kind of jostled back to like that. So domains, hopefully that makes sense. Magnetic field points in the direction that a north pole would go. Remember, if you have, okay, a current carrying wire has a magnetic field around it. Remember, the magnetic field is actually a circular loop that goes around. But if I wanted to represent this 3D thing on 2D paper, well then on this side you would do your first right-hand rule. So remember to do your first right-hand rule. It would be like your thumb is going this way, and then you curl your fingers. So if this is my wire right here, if that's my wire, and my current's going in the direction of the pencil, above it, my fingers are pointing into the page. Below it, they're pointing out of the page. So in this case, over here you would have X's to represent in, and then over here you would have dots to represent out. But it is a loop going around. If I had a loop, okay, and let's say that the current is going around counterclockwise, inside that loop, the magnetic field would be coming out. If I had, let's say, a wire, so I have a wire that's this orientation where it's kind of going straight up and down, where the current's going into the page, well then into the page, and then my fingers would curl in the direction of the magnetic field, so the magnetic field would loop around like this, and it would be that direction. Okay, so that's first right-hand rule. To find the magnitude of the magnetic field, you would have to use this formula. And yes, this formula is on your formula sheet. This is a lovely formula to find the magnitude, to find the direction. You would have to use your right-hand rule stuff. Okay, we did problems where what if you have more than one wire, and I ask you to find the magnetic field. So let's say I have a wire going this way, and with current going that way, and let's say I have a green wire with current going that way, and then I have a purple wire with current going also that way. And then let's say I ask you to find the magnetic field here. Okay, well then you'd have to do your right-hand rule for all the different points. So from the pencil wire, it would be pointing in. From the green wire, it would also be pointing in. And then from the purple wire, it would also be pointing in. So then I would have to use this equation 3 times and add them up. Why? Because they're all pointing in at that point. If it was over here from the pencil wire, it would be pointing in. From the green wire, it would be a dot. And then from the purple wire, it would also be pointing in. So then you would add the pencil and the purple to that equation, and then you'd subtract the green. And then it's always bigger minus smaller, and you'd have to include direction. But hopefully that makes sense, okay? That a current carrying wire has a magnetic field around it. We know that two magnetic fields interacting will give you a force, okay? That you're going to get attraction or repulsion. And we also know that you have a current carrying wire, which means if you have a current carrying wire in a separate magnetic field, it's going to experience a force. Okay, so that, a current carrying wire in, a separate magnetic field, like from a magnet, okay, you're going to get a force. Okay, and this is the basis behind motors, behind speakers, behind lots of different things, how that works. But let's say I have a current carrying wire going this way, and then I don't know, I have a magnetic field that is going to be a bunch of X's. Okay, to find the direction of the force, you would have to use your second right-hand rule. Thumb points in the direction of the current, fingers are straight, point in the direction of the magnetic field, and then your palm points in the direction of the force. So this example, the force would be to the left. Okay. If you had a problem like, I don't know, let's say something like this. Okay, you have a horseshoe magnet, North Pole, South Pole, and then the wire is coming out of the page, so that would mean my current's coming out. So you would go thumbs out, fingers going north to south, and then my force in this case would be that way, okay? But that's how you would find the direction of the force. To find the magnitude of the force, you would have to use this equation, which is, if you look on the equation sheet, this is how it's written, and we'll talk about that. Okay, this is the way that's written on the formula sheet. And here's what this formula is telling you. Number one, anytime you see absolute values, it's telling you this is a lovely equation to find magnitude, but not such a lovely equation to find direction. To find the direction, you got to use your second right-hand rule like we were talking about. And it also tells you that this theta is in between I and L. Okay, most of the time when I did it in class, I just wrote this, BIL sine theta. Okay, but that's how it's on the equation sheet, just so you have it. Okay, so BIL sine theta. We did problems just like we did before, where we had two wire problems. So let's say I have a pencil wire going this way, and then I have a green wire also going this way. And the question is, determine the magnitude and the direction of the force on the pencil wire. Well, where the pencil wire is, there's a magnetic field. That magnetic field is coming from the green wire. So if I do my first right-hand rule, my thumb is pointing here, and you can see my fingers pointing in. So I would put X's on top of this wire. In fact, there are green X's every place above that green wire, but I'm only worried about the magnetic field where this wire actually is. So if I wanted to find the direction of the force, it would be here, it would be here. So the direction of the force on the pencil wire would be that way. Well, that means the direction of the force on this wire has to be equal and opposite. So it'd have to point up because of Newton's third law. But if I wanted to find that force, I would say, well, that force is equal to the magnetic field from the green wire times I times L, and then sine, it would be sine of 90. But then the B, the reason I wrote the B in green was because it comes from the green wire. To find B, you would have to use this formula from before. Okay, so you could do it that way, and hopefully that makes sense. We then talked about, well, what is current really? Well, current really is charge per time. And yes, this equation is on your equation sheet. Okay. So that if we look at our equation, which was F equals I L B, or BIL, but on the equation sheet it's written IL sine B. But if we look at this, well, this is really charge per time. And then I have L, well, I could also say, instead of L, like a distance. And then B, well, if you look, I have D over T. So really, I end up with QVB. Okay. On the formula sheet, it's written this way. Okay. So yes, that's how it's written there. And what this is saying is that, you know what? You don't need current. You could just have a single charge. As long as that single charge is moving, that single charge moving is going to have a magnetic field, which then means that it could interact with a separate magnetic field and experience a force. The only thing you have to remember when you're doing this is, well, that's the formula you use to find the magnitude, to find the direction of the magnetic field. Your thumb, before, your thumb was pointing in the direction of the current. Okay, well, conventional current is positive charge. So you just have to remember your thumb points in the direction that a positive charge is moving. So if you have a positive charge, so let's say I have a positive charge going this way, and it enters a magnetic field that is going to point that way, well, that's pretty easy. You just go here, magnetic field is pointing to the top of the page, so my force is coming out of the page. So the force would be a dot, okay? Or the positive z direction. Well, if you had a question where it's like this, so let's say I have this magnetic field, and let's say I have a negative charge down here that's moving that way. Okay, well, if you do your right hand rule, this time your thumb, instead of pointing this way, your thumb has to point this way. Your fingers go into the page, so the force is to the top of the page. So the force right here would point this way. Well, that would actually cause this thing to go like this. Well, then if you do it here, now my thumb points to the bottom of the page. Hey, look, my force is pointing inward. Oh, look. That would cause that charge to move around in a circle. So remember, if something moves in a circle, then the net force, in this case it's the magnetic force, would equal the centripetal force. So I would get QVB equals mv squared over r, and you could do a little bit of math there, and you could solve for stuff, and hey, that's pretty cool. And this really led into this idea of a mass spectrometer. Okay, and a mass spectrometer is one of those things that they use like in CSI shows where they find some unknown stuff at a crime scene and they have to figure out what it is. Well, they heat it up and they give it a charge, and then they have to accelerate the charged particles through an accelerator. A really simple one would be something like this, where look, I have a positive plate here, a negative plate here. If this thing has, let's say it has a positive charge, that is a positive, it's going to get accelerated and go this way. Well, in this case, UE would get turned into kinetic Okay? And then you would want to make sure it's going the right speed. So over here you would have parallel plates. And if I have this thing going and I want it to just go at a constant speed through here, well, let's say the top plate is positive and the bottom plate was negative. Well, then I would have a force from the electrostatic stuff going down. And if I want it to go straight, that means I would have to have a magnetic force going up. Sorry, that's supposed to be magnetic. Okay, a magnetic force going up. So that if I set those two forces equal to each other, again, you're not going to memorize stuff. You're going to actually do the math. Hey, look, I get this, and then my Q's go away, and I get V equals E over B. So I can select for certain velocities to make it through. So if the certain velocities that make it through, then they enter over here, where is going to be my detector piece. So let's say I have a magnetic field going this way. Well, actually, let's go back to this, okay? If my force is pointing to the top of the page and my charge is going this way, here, oh look, that means my magnetic field would have to be pointing in here. So let's say my magnetic field over here is also pointing in. I have a positive charge moving this way, and if I wanted to do that, it would enter here and hit right there. And from this equation that we just did, okay, you could figure out this distance, which would be 2 times r, and then you could solve for the mass, and then you could figure out what that molecule is, and then you could solve the crime, hopefully. All right, bye, kids. I'm going to pause there, and we'll finish up after that in just a minute. Bye, kids.